we know what an inverse operation is. An inverse operation is the opposite operation. For instance, if I had the problem x plus 5 equals anything, and I wanted to solve for x, I would subtract 5 from both sides, because addition and subtraction are inverse operations. Or if I had the problem 3x equals anything, to solve it, I would divide both sides by 3, because multiplication and division are inverse operations. But we don't have just inverse operations. We can also have inverse functions. An inverse function is basically just the opposite function. It'll undo whatever I have done. It will have all of the inverse operations and in the inverse order as well. We can use them, we can graph them, we can see how they work in a table. And so that's the first thing we're going to do, is make some tables and show how two functions are inverse functions. So here are two functions. F of x is 2x minus 1. G of x is x plus 1 divided by 2. You'll notice times 2 divided by 2, minus 1 plus 1. They both have inverse operations of each other. Now let's take some x's and plug them into my f function and then use those. I've got 4 x's right here. If I take my negative 1 and plug it in, negative 1 times 2 is negative 2. Negative 2 minus 1 is negative 3. Plug in a 0. 0 times 2 is 0. 0 minus 1 is negative 1. 1 times 2 is 2. 2 minus 1 is positive 1. 2 times 2 is 4. 4 minus 1 is 3. If these two functions are inverses of each other, I should be able to take these y's, plug them in as x's into my new function, and I should undo everything and get back to my original numbers. I should have negative 1, 0, 1, and 2 as my outputs. So let's check. If I take this negative 3 and plug it in, will it undo what I did? Negative 3 plus 1 is negative 4. Sorry, negative 2. Negative 2 divided by 2 is negative 1. It did. I take that negative 1 and plug it in. Negative 1 plus 1 is 0. 0 divided by 2, still going to be 0. It did. I take that 1 and plug it in. 1 plus 1 is 2. 2 divided by 2 is 1. It did. Take that 3 and plug it in. 3 plus 1 is 4. 4 divided by 2 is 2. It did. These two functions are inverses of each other, because when I took those outputs and made them inputs, they returned my number back to normal, back to my start, back to my original. These two tables show inverses. We can see that these x's became the other y's. We can see that these x's became the other's y's. That's how you can show on a table that I have two functions that are inverses of each other. But I can also show you on a graph. I can show you by graphing these two functions and seeing what they look like. So for instance, let's take care of the blue function first. Let's take care of the fx function. If I were to graph those, I would have two lines. So I'd have one line. This one line, it goes to the point negative 1, negative 3. 0, negative 1, 1, 1, and 2, 3. And I connect the dots. I can do a quick freehand line. Let's do the red one. If I graph the red function, I pass the point negative 3, negative 1. I pass the point negative 1, 0. I go to the point 1, 1. I go to the point 3, 2. And I can freehand draw another line. Not the best, but I have these two lines. Now, these two lines, if they are inverses, should reflect each other. because if x equals y, y equals x, they're going to be reflections of each other, but not over the line x, not over the line y, but over the line x equals y, over the line y equals x. That's a perfectly diagonal line, slope of 1, that goes from corner to corner through the origin. It goes to the points where I have 1, 1, or 2, 2, or 3, 3, or 4, 4, or 5, 5, or 6, 6, or negative 1, negative 1. Got a little off right there, but you see. These two lines are reflections of each other. Now, it's not the best because I freehand drew them, but you can see that if I were to go down, we'll say here, 1, 2, 3, 4, I should be able to reflect it and go 1, 2, 3, 4, and be on one line and be on the other. There's my reflection. If I go down 4 and across 4, I've hit my line. If I go down 1 and over 1, I've hit my line. That's how I can show you that they are reflections of each other. So I can see it on a table. I can see that I have one table that's x and y, and another table that's the exact same, just y and x. I can see on a graph that I have two lines that reflect over an axis, specifically the y equals x line. And I guess that's what we'll put right here. We should see a reflection. Over y equals x. We can see it on a table. We can see it on a graph. So if you want to find inverses, that's your goal, is to make a table and make a graph and see that. Now we can also do it algebraically, but for the first practice, let's just work on building some tables and building some graphs, basic stuff. By the way, we got to get ready for AP, pre-calculus, not pre-AP, AP, pre-calculus. And that means if I have fx and gx and they are inverses of each other, we don't want to call it g of x. That makes it seem like there are two separate lines, but these are together in one kind of family. So we don't want to say we have fx and gx. We have fx, and that gx line we have, we're going to rename, and we're going to call it f inverse of x. That way, the f line and the f inverse line are connected. These two belong together because they undo each other. Now I'm going to skip this part right here. It's not important for what we're doing right now. We're going to focus on that for the second question. But I will tell you that all these answers, the domain and range for each of these is all real numbers. And in case you forgot how to put that in set notation, you do the squiggles, x, line, x, element, and the r for real numbers. And that's going to be for all these. But right now it's not important. It's going to be important on that second question. So we'll get there when we get there. Let's get there. We have our square root function because we are in the radical unit. We are in the square root and cube root unit. So we have a square root function. We want to make two tables, one for the original and then one for my inverse. And you don't know what the inverse function is, but that's okay. If you can make the original table, all you have to do is invert it. So that's your first job. Make a table for the original function and then invert it to get the inverse function table. Go ahead and pause it right now to try that. If you get stuck, unpause and wait just a second, and I'll go ahead and show you how to start it, and then you can pause it and try it. So, pause. Okay, so for those of you that got stuck, we normally just build a table saying, hey, x is 0, x is 1, x is 2, x is 3. But the problem is, when I plug in a 0, and I first do 0 plus 4, I can square root that. 0 plus 4 is 4. 4 has a square root. But if I use x as 1, 1 plus 4 is 5, and I can't square root 5 and get a whole number answer. If x was 2, 2 plus 4 is 6, and I can't square root 6 and get a whole number answer. If x was 3, 3 plus 4 is 7, and I can't square root 7 and get a whole number. So on 9-3, we talked about knowing what my original parent function table is. We mentioned that my normal parent function, just square root of x, its table is 0, 1, 4, 9. Those x's will always work. And then from that, I can go ahead and take it and say, well, if I plug in a 0, the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. This one is not just the square root of x. It's the square root of x plus 4. Not only that, it is 2 times the square root of x plus 4 plus 1. It has some transformations applied to it. So we mentioned that we need to adjust our x's and adjust our y's. So from this, I can see a couple of things. I can see that we're going to be moving, well, not moving first, we have a vertical stretch of 2. We're going to be moving left 4 and up 1. So I can take this table and use these transformations to create the new table for my f of x function. Pause here if you want to try to check it. Okay, so either you didn't pause it or you did and now you're back. So once we're here, what you want to take a look at is to say, well, vertical stretch of 2, that's a y change. It's vertical, it's up and down. Up 1, that's a vertical change, up and down. The x change is my left 4. These 4 points have to move left 4. If I'm at 0 and I move left 4, I'm at negative 4. If I'm at 1 and I move left 4, I'm at negative 3. If I'm at 4 and I move left 4, I'm at 0. If I'm at 9 and I move left 4, I'm at 5. These are the 4 x's I will plug in to get my y's out. But honestly, I don't even need to do that. I can take these y's and I can transform them to get my y column. I can take the 0 times 2 because it's a vertical transformation, and then add 1 because it's a vertical transformation. 0 times 2 is 0. 0 plus 1 is 1. Or negative 4 plus 4 is 0. The square root of 0 is still 0. 0 times 2 is 0. 0 plus 1 is 1. Works either way. I could take this negative 3, plug it in. Negative 3 plus 4 is positive 1. The square root of positive 1 is still 1. 1 times 2 is 2. 2 plus 1 is 3. Or I could have said my old y of 1 gets doubled, now it's 2, plus 1, now it's 3. My old y of 2 gets doubled, 2 times 2 is 4, 4 plus 1 is 5. Or I could have said, hey, plug in 0. 0 plus 4 is 4, square root of 4 is 2, 2 times 2 is 4, 4 plus 1 is 5. Both ways work. I take this 5, I plug it in. 5 plus 4 is 9. The square root of 9 is 3. 2 times 3 is 6. 6 plus 1 is 7. Or I could have said, hey, that old 3 I had before, that old 3 gets doubled. Now it's 6. 6 plus 1, now it's 7. Both ways work. This right here is my f of x function table. But I also want the inverse. So I'm going to go ahead and take a different color, and I'm going to do the inverse. The f inverse table is the exact same, just reversed. 1, 3, 5, 7. Those were my y's. Now they're my x's. Negative 4, negative 3, 0, and 5. Those were my x's. Now they're my y's. Negative 4, negative 3, 0, 5. And now I have 4 points on each line. And so I'll put those 4 points on my line. Start with the purple one. Negative 4, positive 1. Negative 1, 2, 3, 4, positive 1. negative 3, positive 3, 0, 5, 5, 7, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. There we go. So my line goes like this. Down to the green. I go to 1, negative 4, 3, negative 3, so 1, 2, 3, negative 1, 2, 3, 5, 0, 1, 2, 3, 4, 5, comma 0, and 7, 5. So there's 5, 6, 7, 1, 2, 3, 4, 5. And then I can just kind of freehand that. Something kind of like that. These two look like they are reflections of each other, but I can confirm by putting the line y equals x on my graph. Once again, I freehanded it, so it's not going to be completely 100% accurate. In fact, this line's not even accurate, but you can see that for the most part, yeah, they are reflections of each other. If I am here and I go down 1, 2, 3, 4, 5, and I go across 1, 2, 3, 4, 5, I'm on both lines. If I go down about 1, 2, 3, 4-ish, I should be able to go across 1, 2, 3, 4-ish, and I'm on my line. I can show you that they are reflections of each other. So we see in the table, we built our table from one function and then inverted it to get the second. And I can see that they're inverses of each other. I don't even know what this function's equation is. Now, you might know if you've already looked at the far end of the paper, but right now we don't. Now with linear graphs, all real numbers is my domain and all real numbers is my range. But that's not always the case, especially with square root graphs. So now we got to talk about that purple graph's domain and range. To do that, look at the starting point. 0, 0 is always my parent function starting point. And that 0, 0 point became negative 4, 1. So my starting point is negative 4, 1. That means that my function has a domain that starts at negative 4 and a range that starts at 1. But I have to ask myself, am I going positive or going negative? Am I going up or down? Am I going left or right? That purple function is moving to the right. If it's going right, that means I have a positive domain. I'm going from, bracket, negative 4 to infinity. That purple line is going up. If it's going up, that means I have a positive range. I'm going from 1 to infinity. If my purple function starts at negative 4, 1, that means my inverse function starts at 1, negative 4. So since I have the inverted point, since I have the x and y switched, that means that my domain and range will also be switched. That graph starts at 1. It's going to the right. So my domain is 1 to infinity. It's the same as my range, but what was y is now x. That function's range starts at negative 4, and it's going up, which means that my range starts at negative 4 and goes to infinity. It's the same as the domain, but what was x's are now y's. To get the domain and range, find the domain and range of your parent function, or it's not parent function, but the original function, and then invert that. Although there was one key word right here that is in capital letters, that is pretty bold right there, it is restricted. What does restricted mean? Well, we gave you the inverse function right here. This is the inverse function of what we started with. 2 times the square root of x plus 4 plus 1. Inverted becomes 1/2 times x minus 1 all squared minus 4. You'll notice times 2 times 1/2, inverse operations. Plus 4 minus 4 plus 1 minus 1, square root squared. We see all of the inverse operations. If I put this graph and what we put on our table into Desmos, it looks pretty much the same. That's what we have. But if I put the function we provided into Desmos, notice it's a parabola. It keeps on going. It doesn't stop at the vertex. It keeps on going. But in class, this was the analogy we used. Say you're at home and you look in the mirror. You should see your reflection. But if I look in the mirror and I see my reflection and somebody else's, and I turn around and nobody's there, there is a problem. My house is haunted and I need to leave immediately. If I give you the whole parabola, that parabola does not completely reflect. There is no additional reflection right here. There's no rest of the parabola. So we have to restrict our domain to match only what we have. So we don't do the whole parabola. We only reflect what can be reflected. When we restrict the domain, we are saying there's no reflection for that portion, cut it off, don't use it. Only use what can be reflected, and the rest of this parabola can't be reflected. Restrict your domain. Normally that's not an issue, but you might find a couple problems where it does become one. It's more of an exception than it is the rule. So right here, we have no problem. My purple and my green perfectly reflect each other. So we're done. That's what you do for a table. That's what you do for a graph. But the question now is, okay, if you give me this function, how did I get that? How do I know that's the answer? Yes, it has all the inverse operations, but how do I know that is what I should have gotten? To do that, we got to think algebraically. So let's do that. Let me zoom in on example 1 and the directions. So here's the method to solving problems. The first thing I want to do is make sure that I've taken it out of the letter and put it into y equals. This is an fx graph. But if I want to solve it, I'm going to turn it into a y equals. The second thing I want to do is switch x and y. And I can do those two in one step. The reason we switch x and y is because the inverse has x and y switched. So when we solve the problem, we want to start with that. So my problem is y equals negative 2x plus 5. And when I make the switch, now it's x equals negative 2y plus 5. Nothing changed except for x and y's position. And now comes the algebra. We solve for y. To solve for y, I'm going to pretend like x was a number. X is 20, and I'm going to start solving it. X is 19, and I'm going to start solving it. X is negative pi, and I'm going to start solving it. The first thing I would do to solve this problem to get y by itself is subtract 5 from both sides. That'll cancel. And I don't know what x minus 5 is, so I'm just going to write x minus 5 equals negative 2y. Now I need to know what y is by itself. So my next thing to do would be to divide by negative 2. That'll cancel. And y equals x minus 5 divided by negative 2. So you notice, minus 5 plus 5 divided by negative 2 times negative 2. I have inverse operations. That could be the inverse. Now I say could be. I know that's right. We just worked on it. But just because I have the right inverse operations does not mean it is the inverse. This, in pink, is wrong. That problem also has divided by negative 2. That problem also has minus 5. But here, x minus 5 altogether is getting divided by negative 2. Over here, it's just the x that gets divided by negative 2. That throws the problem off. Just because I have the correct two operations does not mean it is written correctly. I want to show you in just a bit how to know if it is right or if it is wrong. But let's continue with building. That is a good answer. If you gave this to me on the group quiz, if you gave this to me on the test, I'd probably give it full credit. But the problem is, that's not an AP pre-calculus answer. That's good for regular or on level. That's good for basic, but that's not the advanced answer. The reason is, y equals does not connect it to the fx we started with. If I'm dividing by negative 2, do you know what the transformations are? Do we know what a, b, h, and k are looking at that? That's not wrong for the inverse, but it's not cleaned up. And so we need to clean it up. How do we do that? We put it back in transformation form, and we make the y into the f inverse of x. And I can do those two steps together. We don't divide when we do transformations. We've always multiplied by the reciprocal. So don't divide by negative 2. Multiply by negative 1/2. Y becomes f inverse of x. And this becomes negative 1/2 times x minus 5. And this is your advanced answer. That is the correct AP pre-calculus answer. The f inverse of x is negative 1/2 times x minus 5. We took my original. We switched x and y's position. We solved for y, and then we cleaned it up. And this function undoes everything that my original function did. That is how you find the inverse operation, so the inverse function algebraically. And I'll do the same thing for the g function. I'll follow my same steps of switch x and y, solve for y again, and then clean it up. So take a moment, pause it, give it a shot, and when you're ready, unpause it for the solution. Welcome back. Okay, let's go work this one. To begin with, I'm going to take care of those first two steps simultaneously. What is my function to solve? It is x equals 3 times x minus 5, y minus 5, I'll just copy. Y minus 5 squared plus 4. And now I need to solve for y again. First thing I would do is subtract 4 from both sides. That'll cancel. And I have x minus 4 equals 3 times y minus 5 squared. Next thing to do is divide by 3. So divide both sides by 3. That'll cancel. And we have x minus 4 over 3 equals y minus 5 squared. The next thing to do would be to take your square root. Square root of all this will cancel. Square root of all that. Now I have the square root of x minus 4 over 3 equals y minus 5. And the last thing to do would be to add 5 to both sides. So the final answer, which I'm running out of room for, is y equals the square root of x minus 4 over 3 plus 5. And that's not a bad answer, but that's not the answer I want, because that's not cleaned up. So I'm going to clean it up, and I'll put it kind of right here in the middle. Yeah, I'll put it right there in the middle. So there's my answer, but when I clean it up, I'm going to make it, now you know what, I lied. I'm not going to put it right there. I'll squeeze it down below. That function would become no, not f, sorry. Oh my God, I'm messing most of that up. It's at the end of the day, it's late. All right, now it is g inverse of x, because we started with a g function. Always link them. So that g of x now becomes the g inverse x. And it is the square root of 1/3 times x minus 4 plus 5. I took that divide by 3 and made it times 1/3. But it still has all the inverse functions. Instead of times 3, I'm going to times by 1/3. Instead of minus 5, I got plus 5. Instead of squared, I have square rooted. Instead of plus 4 up here, I got minus 4 down here. I have all inverse operations. So there's your best answer for that problem. And as you can see, you might want some scratch paper in order to work some of these, because we kind of run out of room if we're not careful. So there's the answer. One more time, try that with example number 3. I have this cube root function, and I want to know what is its inverse function. Pause it, try it, and we'll come back when you're ready. Welcome back. Okay, let's try to do better on this one, because I messed up that one a couple of times. So we're going to start with my original, but I'm going to flip-flop x and y. So we have x equals 4 times the cube root of y minus 5 minus 2. To save some space, I'm going to go ahead and take care of the first two together. I know the first thing to do would be to add 2 to both sides. And after I add 2 to both sides and get x plus 2, I'm going to divide that by 4. So we end up with x plus 2 over 4 equals the cube root of y minus 5. So that canceled, and that canceled. Now I'll take care of the next 2 steps together in one. I know that the next thing I should be doing is cubing both sides. And when I cube both sides, that'll cancel the root. And then when I'm done, I should add 5 to both sides. So I end up with whatever x plus 2 divided by 4 cubed is, plus 5. And that's my y function. I added 2 first, then I divided by 4. Then I cubed everything, and then I added 5. And that's not wrong, but it's also not right. It's not cleaned up yet. It's not the best answer. I should make it so that it is in transformation form, and so that it ties back to my original. My original was an h function, so this answer needs to be an h inverse function. I don't want divided by 4, So I'm going to change that to multiplication times the reciprocal times 1/4. So my final answer is 1/4 times x plus 2, all getting cubed, plus 5. And there is my best answer, because it is in transformation form. It is tied back to my original h function. That is what I want. And it has all the inverse functions. That plus 5 will cancel the minus 5. That plus 2 will cancel the minus 2. That times 1/4 will cancel the times 4. The cube will cancel the cube root. I have all of the pieces I need. Now, how do I know that I properly did it? Because, yeah, I've got all the right components, but how do I know it's done correctly? We show it algebraically using composition of functions. If you remember from the first day of the unit, we said that we can take any number and plug it into a function, and I can work that out, and then when I get an output, I can take that number and plug it into a different function. I can continue chaining functions together by taking the answer for one and putting it into another. The output becomes the new input. In fact, we did that at the very first problem. We said that the output we got from one table became the input for the next. We linked these two functions together by using composition of functions. And now we're going to do the same thing algebraically. We're going to prove that the two f functions, the f and f inverse, are indeed inverses. And we show it by saying, if I were to take the inverse and plug it into the original, or if I were to take the original and plug it into the inverse, no matter which way I take it, both ways, I should cancel everything and have only x remaining. Everything else goes away. So let's take the f and f inverse functions and put them together. The f function, negative 2x plus 5. The f inverse function, negative 1/2 times x minus 5. I'm going to take these two functions and put them into one by plugging one into the other. And I probably should have changed colors to have some kind of differentiation. Let's do that. I'll do blue. Negative 1/2 times x minus 5. So what I'm going to do is take this blue function and plug it in where x goes. That means that the negative 2 is still there, but now, instead of x on the inside, I have negative 1/2 times x minus 5. If I were doing this, you could say, well, I can't do x minus 5. I can't simplify that together. I can't use PEMDAS because p parentheses, I can't do x minus 5. But I can distribute this negative 1/2 to both of these. And you're not wrong. But immediately after you distribute negative 1/2, you would distribute negative 2. So question for you. What is negative 2 times negative 1/2? It's just 1. If I multiply by negative 1/2, and then I multiply by negative 2, I've just undone what I did. I've put it back to normal. It turns out that these two cancel each other out. And all I have left is x minus 5 plus 5. Well, if I take a number and subtract 5 from it and then add 5 to it, I've done nothing. It's 0. It cancels out. It turns out that all that's left is just x. I know those two are inverses because when I plugged one into the other, I got just x behind. So let's take a look at example number 2 now. We're going to use the g and the g inverse to go ahead and create this proof to make sure that we have two inverses, two functions that are inverses. We're going to start with, we'll keep with blue. The original, 3 times x minus 5 squared. 3 times x minus 5. 5 squared plus 4. And then our inverse function, the square root of 1/3 times x minus 4 plus 5. I'm going to take what we got here, and I'm going to plug it in where x goes. So what we have is the original 3 times all the green minus 5 squared plus 4. There's my original function, but the x is not just x anymore. The x is all of this green. The x is the square root of 1/3 times x minus 4 plus 5. So I took the original and put this green function in x's place. And I see a couple of things right now that cancel. I see that this plus 5 and minus 5 will cancel out, because if I add 5 and subtract 5, nothing happened. I see that I have this square root getting squared. Those two cancel. If I cancel both of those right now, what I have left is 3 times 1/3 times x minus 4, chop chop, plus 4. Well, 3 times 1/3 will cancel out, which means all I have left is x minus 4 plus 4. And if I subtract 4 and add 4, nothing happened. X is all that's left. Example number 3. Pause for a second. Go ahead and try this one. See what you can do with it, and unpause when you're ready to check out the answer. Welcome back. Okay. In blue, let's take a look at the original h function. The original function was 4 times the cube root of x minus 5 minus 2. 4 times the cube root of x minus 5, put a 3 there, minus 2. Now, I'll go ahead and take the inverse function we found, which was parentheses 1/4 parentheses, wrong way. Try the other parentheses. Let's delete all that. There. I'll put more than I wanted to. 1/4 times x plus 2 chop chop cubed plus 5. I'm going to take this green function and put it where x is. So we're going to have all of the original we had before. 4 times the cube root of all that, minus 5, minus 2. So let's take our green and put it in place. Our green is 1/4 times x plus 2, chop, chop, cubed, plus 5. And I see a couple of things that are going to cancel. I see plus 5 minus 5 will cancel. I see this cube root and this cube will cancel. If I cancel both of those things right now, I'm left with 4 times 1/4 times x plus 2, chop, chop, minus 2. And 4 times 1/4 cancel out, which leaves me with just x plus 2 minus 2. And if I add 2 and subtract 2, nothing happened, which means x is all that's left. That's how I can prove to you that two functions are inverses. Now, if two functions were not inverses, then I would not have just x by itself. I would have x plus 4, x minus 2, 3x squared. I would not have x by itself. So when you do these, you want to make sure that you have the correct inverse. And how do you know? You plug one into the other, and you see if x is all that remains. There are 4 practice problems down below. I'll have to make a separate video for these because it is 5:05. I got to get out of here. So the notes are done. The notes video obviously will be posted. You're watching it right now. Makes sense. These 4 practice problems will be recorded later. So you can get these, but give them a shot. See what you can do with them. Check your answers when that video gets posted. And until then,